Alright, so today we're going to solve problem number 2.26 from Proper Do It. It's a long problem, it's a 4-part problem, so I would recommend you read the problem first before you see this video. But briefly going over what's given in the problem, we have a wall here. Let me try to see if I can get a better marker. But we have a wall with one end adiabatic. It's a long wall and a wide wall, so it can be treated as a one-dimensional problem. You have some cooling going on this surface. A heat transfer coefficient is given to be equal to 500 watts per meter squared Kelvin. We also know the temperature of the air here. It's given to be 200 degrees Celsius. The wall temperature at this location, let's call it T wall, is given to be 120 degrees Celsius. The thickness of the wall is given to be 50 millimeters. So we're going to write it in terms of meters. So raised to the power minus 3. And it is also given that there is some heat generation inside, some Q dot. This is something that we actually want to find out in this problem. So the first part of the problem is to actually estimate what this Q would be. We are also given that the temperature profile is of this form. Where the constants A, B, C are not known, and one of the objectives of the problem is to estimate what happens, what the values of these A, B, and C are. And then we also try to estimate what happens, the influence of the temperature profiles inside this wall with the heat transfer coefficient varied and the heat flux generated varied. So let's start solving this problem. Let's first set up our coordinate system. Call this the x-axis here, the y and the z-axis, which are not relevant at this point. Let us also define a control volume here, a small control volume, just outside the wall here, going all the way to just outside the wall at the other end as well. So if you try to set up an energy balance here, you have an energy generated term here, Eg. There's an E out that goes here. It is given that it's a steady state problem, so there is no E stored and there's no heat coming into the control volume here, so E in is 0. So writing down the energy balance equation, we have E in minus E out plus E generated is equal to energy stored. It's a steady state problem. This goes to 0. There's nothing coming in. So we have energy that's being generated there is the energy leaving the control volume. We know what energy being generated is. It's the Q dot that you see there times the volume that you're considering. Let us call this length to be L. It's also given that the generation is uniform, so we multiply that by the volume that is being considered, which is nothing but the area here A times this length. The energy leaving the control volume from this surface, it's because of convection, and so we have a convective heat transfer coefficient H. You have the area of transfer, the same area of heat transfer there, times the difference between the wall temperature and the air temperature on the outside, the surrounding temperature. So with this we should be able to estimate what Q dot is, and Q dot should be the heat transfer coefficient times the difference between the wall and the surrounding temperatures divided by the length or thickness of this wall. So let us call this equation 1. We will come back to this equation several times, so even if I do erase this equation, just note down that this is called equation number 1 here. Now substituting the values for the heat transfer coefficient, it's 500 watts per meter squared Kelvin, 120 minus 20 degrees Celsius times 50 10 to the minus 3 should give us the generation term to be 10 to the power 6 watts per meter cube. that's the answer for the first part of the problem. Now let's try to estimate what these coefficients are, which is basically the second part of the problem. So I'm going to go ahead and erase the energy balance equations here. So now let's look at the boundary conditions. We have one boundary condition here at the adiabatic wall. We have one here at the wall facing, which is convecting out to the environment there. So the boundary, and that's known from the temperature here. The other one's known from the slope here. So writing them down, the first boundary condition is T at 0. Remember, our coordinate system starts from here, so this is 0 and this is x is equal to L, is T wall. Our second boundary condition is the rate of change of, let me use the full derivative here, so at x is equal to L is 0 because it's an adiabatic wall there. We still need another equation to estimate all the three terms. Now for that we need to go to the heat diffusion equation. So if you look at the one-dimensional heat diffusion equation, we have K times d squared T by dx squared is rho Cp they are partial derivatives for now. We know it's steady state, so this goes to 0. And so rho squared T by dou x squared, or the absolute derivative here, is, so we have three equations here. Let me call this 2, 3, and 4. And we have three unknowns, so we should be able to solve this problem. So substituting x is equal to 0, we have T0 is A equal to T wall, which is equal to 120. Now let's look at the equation number 4 here. We take the derivative with respect to x twice of this equation. We should be getting d squared T by dx squared is 2 times C is negative q dot by k, or C is negative q dot by 2k. So let's call this 5, and this results 6. So I'm going to have to erase part of these equations, but we know what C is, and we know what A is, and we need to find what B is. So B comes from this equation here. So let's take the first derivative of this equation here, and that should be B plus 2 times C of x at x is equal to L is 0, or B is negative 2CL, which is negative 2 times Q dot by K times L, which is, I'm sorry, there's a 2 down here, so it's Q dot L by K. So now we know, let's call this 7. So we know what A is, what B is, what C is. Substituting the values for Q dot, which is 10 to the 6th watts per meter cube, we have, for this case, A is equal to 120. This is, the units would be degrees Celsius. B is 10 to the 4th degrees Celsius per meter, because remember B is multiplied by another length unit here, and then C is negative 10 to the 5th degrees Celsius per meter squared. So that should give us the temperature profile inside this wall. So let's try to sketch it first. Try to be a little consistent here. So if this is the x-axis, temperature profile, and it's being cooled on this surface, so we expect the temperature profile to be this way. Somewhat increasing and becoming adiabatic at this point, so you have the slope being 0 here. This we know is 120 degrees Celsius, and by substituting these values here, this location is estimated to be 370 degrees Celsius. So, as you can see here, there's no heat transfer here because the slope is 0, the variation of temperature with respect to length is 0, and so there's no transfer in this direction. Heat is being transferred in this direction, and at this location, it should be equal to the heat transfer into the ambient here. So let's look at this third part of this problem. So the third part of this problem is, if this heat transfer coefficient is reduced or is halved, what happens to the temperature profile? So for this, we go to the first equation that we had used, or equation number 1, which was